we've opened up to a wide audience. So we've currently got about 115 people on the call. So many thanks to all of you for joining in and taking part. There'll be more webinars, and I'll present those. I'll let you know what's happening in the future at the end of this session. But please feel free to distribute the links, share the information with your colleagues, and pass the word around. The UK Climate Programme is instrumental in supporting businesses, local governments, policies, local government, national government. The data produced by the UK Climate Programme are widely used and are seen as the exemplar way to undertake a national level climate change assessment. So we're in a very fortunate position that the UK Climate Programme has been going now for I've been involved in it since 1991 in various forms, and it's been expertly managed by the Met Office and its partners ever since. So without much further ado, I'd like to just introduce you to our two speakers. We have Paul Young from JBA and then Ben Harrison from the Met Office. Paul is the lead scientist from JBA Risk Management, and prior to joining JBA at the end of 2022, Paul was a senior lecturer at Lancaster University, where he headed up an interdisciplinary research group focused on climate science, air pollution, data science, and their interface with policy, business and community. So JBA, well known to me, excellent organisation doing some fantastic work. So Ben, over to you. Paul, over to you.
Thanks very much. Yeah, real pleasure to be here. Yeah, I know we weren't supposed to get political, but I posted something on LinkedIn about this, and I can still wear my university hat where if I want to say something political. And yes, I totally agree with everything you've just said. So David, do I presume I should be able to advance the slides? Should I, or shall I just ask you to advance them? Are you controlling from your end?
Nihar Osislali is going to be presenting.
Okay, great. I shall. Okay, so good afternoon, everybody. So yeah, as David said, so my name's Paul Young. I started at JBA Risk Management nearly a year ago now, having moved from academia, and I've got just an overview presentation about how we use flood data, or information from UKCP to say something about flood risk in the future. Is someone unmuted? David, it might be you actually. I think I'm just getting some feedback on your line. Thanks. So just want to say, as we're standing in academia, actually, what I'm presenting today is not my work at all, and it is very much the work of all my brilliant and very clever colleagues. So yeah, could we advance the next slide, please? So today I just want to give a very brief overview for those of you who don't know, just to say who JBA Risk are and what we do. It's totally not, this isn't a commercial presentation, let me be clear, you're not going to get an advert from me, but just so you can situate us a little bit. Then I thought I'd show you just a selection of results from how we've used UKCP data to say something about UK flood risk in the future. And I hope you agree, I mean, we're not the only people doing this, of course, but I think this is a really cool data set, and we can do some really cool things with it. Yeah, and as I was asked by the organisers, just to want to say a little bit about something about what our experience of using UKCP data is, and just some, I wouldn't say issues, but just things that we've come across as we've been working through it. Next slide, please. So JBA, we're part of. There's a lot of companies that I guess are out there that work in environmental risk, and so our specialism is floods. That's why we're kind of known as the flood people. You see from our logo up in the top right. And the basic thing we produce are detailed flood models for everywhere in the world, and flood from river, from surface water, so rainfall, and in many locations coastal flood information as well. And so this is a very data-hungry process. It's sat on a huge framework of several different types of models as well. So if we go to the next slide, please. So just to, this, I've said I'm going to keep this really quite high level with the overview. I won't give you any equations or anything, but we're very much in the business of translating climate science and translating environmental science into information for end users. And I'll say a bit about who those end users are in a minute. So we take climate data. So for the UK, that's obviously our UKCP data, hence I'm talking to you here. We use that to get some information about weather, how weather might change in the future. So changes in risk from different types of storms or different river flows and things like that. We then translate that through hydrology models and hydraulic models, and really detailed information about how the surface of the Earth's elevation is, to say something about how floods would spread out, and how that will impact locations, properties, assets, and anything like that. And then we can also say something about, well, if we were to include some flood barriers or any other kind of mitigation, how that might protect against the flooding that we show. And we can also use the output from our models, not only just to give you a flood depth at the location, but to say something about costs and damage. If you go to the next slide, please. And that's important. Our main clients include the insurance industry, and in the reinsurance industry. So that's the insurers of insurers, basically, banking and lending, people involved with asset management, and also globally, people involved with international development. You can go to our website, web address is down in the corner if you wanted any more information on that, and or I'm happy to answer to questions at the end. Next slide, please. So just to say a little bit about climate change, I try to include some bit of climate science, as I'm a climate scientist. So from a flood point of view, one of the really important things is that as the atmosphere warms, as we add more greenhouse gases to it, the atmosphere can hold more water vapor. And many of you on the school will know this already, but there is a relationship known as the Clausius-Clapeyron relationship, which says, all things being equal, for every degree in temperature that the atmosphere warms, it holds 7% more water vapor. And if we hit the next bit, so what that means, again, all things being equal, there's a lot of complication to this, is that we expect that as the atmosphere warms, the rainfall events will become heavier. We're loading the dice, is one way of thinking about it. For every rainfall event that we get, it will be wetter than the equivalent event would have been in a cooler atmosphere. And this is what we see in observations. This is taken from a 2015 paper from Fisher and Nutty. I just redrawn it here. And they looked at locations all across Europe and looked at the extremes in rainfall. So these are what we call the 90th percentile, 95th percentile, right through here to the 99.9th percentile. So this is stuff. So 99th percentile is, in this case, that's like happening once every, I think 100 rain events. I think that's how they did the data. And they showed how these extremes have changed over time. So between those two time periods written at the top there, so 1981 to 2013, roughly present day, this is a slightly older paper, compared to a time around the middle of the 20th century. And you see this increase in rainfall. And if we hit the next slide key again, we can see that this is exactly as expected from climate change. So if we know, as I said, like as the atmosphere warms by 1 degree, we get 7% more water vapor. If we just do a very rough back of the envelope calculation and assumes that all just translates to rainfall, you actually get the warming, which is very close to the observation. So that shows, thermodynamically over large scales, this really does bear out, and you can really see that climate change has been impacting extreme rainfall events. Next slide, please. So just want to say a little bit about the workflow that we have and how we use UKCP data. Again, I've kept this very, very high level. There's obviously a lot of detail, a lot of people working on this, and that's not, of course, to denigrate the complexity of it, but I just wanted to give it as a something that's hopefully digestible. So UKCP data enters in the start of our workflow when we're thinking about climate change in the future. We do some statistical processing of that, involving things like extreme value theory, etc. And we use that to push broadly towards two products. So one, we can push the output from our statistical processing into our current framework to say something about how future flood depths might change for a given location. And then we have a whole bunch of metrics and statistics, analytics, as it gets sometimes called in the industry. And so we can say, for a given postcode, a given property, We expect its risk to river flood or coast flood or from surface water rainfall type flood to increase by this amount, or to have a rough cost of this amount. And then secondly, we have what we have in our industries known as catastrophe models, and this is much more of a statistical based approach, where you essentially simulate a very long, thousands of years time series of the UK, and you fire a bunch of different weather events at it, which have been appropriately scaled according to climate change. And that's to look at things at a much more kind of what we call portfolio level, or the whole country level. So you typical questions that might get asked here are like, oh, well, I'm a reinsurer. In the portfolio, I've got all these properties everywhere. What's the loss in monetary terms that I could expect every in a one in 200 years, or if you like, 0.5, got a 0.5% chance of happening in one year, and how will that change with climate change? Next slide, please. So I'll just show you just a couple of bits of output that we can do from this framework, from using the UKCP data as input. And this here is showing the number of UK postcodes. I've done it normalized, just for kind of ease of reading, and the number of postcodes which are at risk from flooding, and how that changes for different scenarios and changes over the century. So many of you, I guess, will be familiar with the alphabet soup that is climate science, but these scenarios that are provided by UKCP and are used in analysis throughout the literature, the representative concentration pathways, RCPs, and then the numbers, without going into detail, the higher the number, the more the warming. So as you go from 2.6 to 4.5 to 6.0 to 8.5, there's more warming globally, and for what comes out in the wash here is that the warmer the climate scenario, the more the damage, and as we progress through the century, you see that damage increasing. Again, I'm not going to go into any detail of the analysis here, but just a kind of example of how we use the UKCP data. Next slide, please. And I talked about how we can use this in a catastrophe modeling framework. And this just shows you an example output from that. Again, so looking at a baseline, so a present day. This is from we have a standard portfolio which we just use to generate these examples. Of course, a portfolio from a particular reinsurer or another client might look a little bit different. But this just shows you that we can use UKCP data through our framework to calculate numbers like this, which are of huge interest to our insurers. So this is the annual average loss that they could expect, well, for this given portfolio, for these different types of flooding. So flooding from river, flooding from rainfall, the surface water flooding, and flooding from the coast. And you can see, like, moving from baseline, if we go across straight to RCP 8.5 at 2050, the average annual loss just from river is the same from all losses at the present day, give or take. And again, of course, those numbers will be very different depending on the portfolio. Next slide, please. So those two examples I've just shown are looking at an aggregate UK level. So one coming through from our analytics and one coming through from our catastrophe modelling. We also can use the output from UKCP data to say something about flooding at particular locations. Again, this is an example that I showed just because it shows some nice maps, and everyone likes looking at maps, or maybe not in this case because it shows flooding. So this is Exeter, and it shows the change in flood risk on the left there. I forgot to put the numbers in. I think this is middle of the century, probably RCP 8.5. Forgive me, I left out that information. And this is will be for a particular return period, so a particular chance of an event happening. And we've just highlighted that dot there, so that shows there's actually quite a large increase in flood risk at that location. But if then we look to the plot on the right, that actually doesn't increase. The flood depth does not actually increase that much. Sorry, there's not a huge amount of flooding at that location. So even though we've got potentially a 25% plus increase in flood depth, there's actually not a lot of flood there. So we need to kind of combine the information about change in risk with the baseline risk. Next slide, please. And again, this is an output that we can get through our loss modeling framework. This is for RCP 4.5. This is the percentage change in losses. Now back to I think considering monetary losses again, for different regions, different aggregate regions this time, split by different hazard types. So flood from river, flood from rainfall, flood from the coast, and how that changes for this given scenario. And here we're looking at a particular return period. This is the 100-year return period, or if you like, an event that would have a 1% per year chance of happening. And that's again, this is all sorts of information that will enters into the analytics engine, the risk frameworks of insurance companies, for instance, or increasingly lenders and other sectors. Next slide, please. So last two slides, I just wanted to say something about our experience of using UKCP. Again, I'm happy to answer any questions. I know I've kept the detail quite up here, but I take this opportunity just to thank the people that have produced UKCP. I think it's a really sophisticated data set, and there's a lot that we can do with it. And we just kind of scratch the surface, hopefully giving you some interesting examples of how it gets used in our risk industry. And we really appreciate the value that's been added with the post-processing of that data. So we can say something about extreme values, for instance, and looking at different percentiles. And it's really easily accessible, and for us to be able to download and easily understandable licensing and things like that. Next slide, please. And challenges is too strong a word. I think, and this first challenge I've highlighted, I think that's this is basically our job. We need to be able to use this data in a way in our framework, and that requires us to do some clever things. Turn the handle on some of our own science to make sure that we can get the UKCP data in a way that we can use it. So that one of the key challenges that we have to think through is interpolating through time and space. Sometimes we have clients who are interested in perhaps time horizons which are not directly output by UKCP. So that's an example for that. The lack of availability of some scenarios is a challenge again, but it's not insurmountable. Some clients will come with particular exotic scenarios or an RCP that might not be output there. There are ways around that. Again, I'm happy to talk about that. And I think what we perhaps this is a gentle bit of feedback. It would be really nice, and sorry if I've missed this, but if there were ways for us to have really clearly communicated where there have been updates to the UKCP 18 product, what the timeline is for the next generation. I believe that's all. Next slide. That's just a small print. If you go to the next slide again, that's just ways if you wanted to get in touch. My email address, which I'm sorry I didn't put on there, I'm paul.young@jbarisk.com. I'm very happy if people have got follow-up questions that they don't want to ask in this forum about our experience of using it, or if you want to talk about floods. Okay, thanks very much. Thank you, David.
Paul, thank you very much. Apologies, the chat has appeared to be not functioning at the moment, so I haven't been able to take in any questions, or at least I've not been able to see any. So what we'll do is move on to Ben, and once we get the chat functioning, we'll then come back to Paul, if that's okay, to ask any questions. So
yep,
Ben, I hope you're there. And yeah, so Ben is a climate and ocean modelling scientist in the Met Office at the Hadley Centre. I don't think I need to introduce the Hadley Centre in the Met Office, of course. So Ben, over to you.
Right. Good afternoon, everyone. Yeah, thanks for joining this webinar. Focused on sea level rise and flooding in the last talk. Yeah, a bit of background about myself. I'm a scientist in the Met Office Hadley Centre in our sea level team. A key responsibility for our team is developing kind of information about the potential impacts of climate change on sea level rise around the UK. If you go on to the next slide. So part of my role involves trying to kind of improve our understanding of the processes that affect sea level, kind of working with scientists at other organisations. So some of these are shown on here. So the kind of title for this talk is about sea level storylines, and it's a way of reframing uncertainty. And the thing that's relevant for these processes here is that with each process, or another way of thinking about it is in the model chain that Paul Young was showing, with every step you introduce additional uncertainty because different models produce different results. I'll go through these briefly. So if we go to the next slide. So firstly, kind of to get the broad scale kind of right, for our global projections, we need to take into account that as the climate warms, much of the excess kind of heat goes into the oceans, which expand, and that raises sea level. And different simulations from different climate models will produce a different amount of expansion. So that gives us a kind of uncertainty range for that process. The second main thing is that adding water to the oceans. So this is transferring water previously stored on the Earth as either ice, or also there's a small contribution from reservoirs. And this process isn't actually included in the model, so we have to make assumptions about how this kind of scales with warming in order to kind of come up with the kind of probability values that were mentioned in the previous talk. So we go on to the next slide. So if we move on to the things we need to consider when we create local projections, we need to think about how the local kind of ocean circulation changes. We also need to think about how when ice or water is moved from the land to the ocean, you're changing the distribution of the mass on the Earth, and this changes the way that gravity and the Earth's rotation, and also the way the Earth is slowly deforming, affects sea level. So for the UK, as the Greenland ice sheet loses mass, there's less of a gravitational attraction on the surrounding waters. So you can have this near field, this sea level fall at locations near the ice sheet. So what this means for the UK is that Greenland doesn't make much of a contribution at the UK, whereas Antarctica does. Secondly, a related effect is that as this ice is removed, the Earth slowly adjusts. And in fact, there's areas in the north of the UK where the land is still kind of rebounding from the removal of ice during the last ice age. And finally, we need to know, well, firstly, what the elevation of our locations are and whether they're sinking. Ideally, we want to know what the processes are, so where areas are subsiding. So if we go on to the next slide.
Ben, sorry, can I just quickly interrupt? Yeah, just for Q&A, I've just been pointed out to me, if we can use the question and answer function, please, on Teams for asking questions. Apologies for that.
All right, thanks, David. Good to know that's working. Right, so hopefully this slide will answer some of Paul's questions. So part of the role in our team is developing information for the UK climate projections. So the last one was in 2018, and our main projections were based on methods from the previous IPCC fifth assessment report. This included extended projections out to 2300, so covering a kind of longer time horizon. One of the things we didn't include was an update to our, I guess, what you can think of as our plausible worst case. And I guess part of my role also involves working with people, other government organisations or other organisations generally, about things that we could include in the next round. And we're working on a new kind of high impact or worst case scenario. So if we go on to the next slide. So because of the processes I kind of mentioned previously, sea level is not uniform globally, and even for the UK, despite being a small country, you can see kind of differences in the range of sea level at, say, London on the right hand side and Edinburgh kind of next to it, where kind of the changes are larger effectively at London, and perhaps not as clearly here. The range also differs slightly, so uncertainty also depends on the location. So if you go on to the next slide, in the previous talk we were talking about flooding. So people aren't just interested in how mean sea level rise is changing. You want to know about the absolute kind of highest water level that could occur at the location, and for that you need additional models which we do some of that at the Met Office, but I guess more common to have that sort of assessment at other organisations. So that's kind of where we are at the moment. And if you go on to the next slide. Yeah, I've covered that. So next slide, please. So I mentioned that a lot of our methods the main projections are based on methods from the previous IPCC assessment report, but there's actually been a more recent one, as some of you will know about, that was released in 2021 that came with new projections. It included extended projections out to 2150, providing an assessment of the global mean change for 2300, which is shown in the kind of vertical solid bars. The shaded regions show the range for low and high emission scenarios, and the dotted line is what happens when you include additional kind of processes related to instabilities in the ice sheet. And essentially, the headline is that 15 meters, in excess of 15 meters sea level rise cannot be ruled out for 2300. So that's quite a considerable kind of range to have to account for, and so they have what they've called storylines that provide a continuous kind of evolution of how that sort of situation might emerge. So we go on to the next slide. So I've talked a lot so far. I've mentioned a lot about uncertainty, but what about what can we be certain about? So one of the things we can't assign a probability to is what scenario we will be on, right? So we can't predict. It's difficult to predict how our mitigation efforts will go over the next century. But if you look at the kind of graphs here showing the projections from the latest IPCC assessment, there's actually not much difference until sort of 2050. So for the first part of for the immediate future, it doesn't actually matter which kind of scenario we're on, the changes are the same, and it's only later that we start to see big differences. The other thing that kind of gives us a bit more certainty is that the projections from UKCP 18, shown in the bars, are in close agreement with AR6, so we can kind of be confident that we're getting similar results. So if we go on to the next slide, there is a kind of key difference. Whereas in the latest assessment from the IPCC, they provide this continuous kind of evolution of how a worst case might evolve, whereas our version of that, which wasn't updated since 2009, just provides information for just before 2100. It doesn't really indicate at the quite large increase that you could see in the beyond 2100. So if you go on to the kind of next slide. So I just wanted to briefly say, why do we have these kind of worst case scenarios? And essentially, to get the probability values that were mentioned kind of in the previous talk, we take the results of different climate models and use, where they agree over a certain range, the number of models that fall into a certain kind of range of changes, we can use that as a measure of how kind of likely that kind of change is. That doesn't really work when you go to the kind of tails of the distribution, because it could be dominated by, say, one model, and so it doesn't really apply as the criteria. So yeah, that's shown there. We can't really quantify tail risk in the same way. So the storylines or plausible worst case is a way of kind of providing that information and working through how these scenarios might affect people's plans. So if we go on to the next slide, what we want is something that's consistent with the storylines provided by the IPCC. However, we want that information to extend beyond 2150 because some people are building or involved in plans or responsible for critical infrastructure that has a lifetime of over 100 years, and they need to consider the risk over the full life cycle. So these are kind of useful for exploring kind of what if questions. We also wanted to not just talk about kind of a worst case, we wanted to consider the full range. So what's the absolute minimum that you would have to adjust for. So having storylines that span the full kind of envelope of kind of possibilities. So if you go to the next slide, so here's an example. So what we've done is, this is our kind of a best case scenario. We take an optimistic scenario where there's quite drastic changes to emissions, and where the sensitivity of the ocean and the cryosphere is lower than suggested by the majority of the climate models we look at. So here, by 2300 globally, you can get sort of changes that about 80 centimeters, and there's quite considerable differences around the UK. So Edinburgh, by 2300, you're looking at sort of 15 centimeters, and sort of 70 for say London and Cardiff. But at the other extreme, we go on to the next slide. So this scenario is based on make similar assumptions to the kind of worst case scenario presented in the 6th assessment report. We're looking at a high emission scenario where the ocean and cryosphere are more sensitive than the majority of models suggest, and also where instability processes are triggered that leads to these kind of runaway contributions from Antarctica. And here, everywhere now, by 2300, you're looking at sea level rise in excess of kind of 15 meters. And I guess the most notable thing is that there's quite a rapid acceleration just after 2100. So that, which wouldn't have been provided by our previous worst case scenario from 2009. And there's a kind of map of how this kind of looks, shown in the bottom corner. If you go on to the next slide, so future work, we want to kind of run these storylines through various other models to look at, if you take that same scenario, how does that affect the kind of regional ocean? How does it affect waves and surges? And I guess the next step of advancement would be to consider a coupled modelling setup. So then you can account for compound events, so both surface and coastal flooding. And I guess the basic idea with the storylines is we're not providing a probability for these particular scenarios. And in fact, that's probably not that different to how the climate scenarios are used, right? You can't say how likely a particular pathway will be, but you can talk about the relative likelihood, assuming that scenario occurs. And it's the same for these storylines in a way. The storyline itself doesn't have a probability, but you can look at differences with those same assumptions. So we go on to the kind of next slide. So we believe these physically consistent storylines provide a means to kind of more fully explore the range of future outcomes, and can kind of aid communication by kind of representing the true uncertainty. Because if you just focus on the center of the distribution, you're kind of ruling out changes that could come from like abrupt changes. So there could be tipping points associated with the ocean circulation in the North Atlantic, for example, or the ice sheets. And also, we want to then sort of look at how we can use this for looking at compound events. So that's all from me, and happy to take questions. And yeah, there's some references to some of the work discussed.
Ben, thank you very much. And everyone, yeah, as mentioned, the questions are available through the Q&A function, which I unfortunately didn't have on my Teams. So I'm just using another laptop at the moment with the questions on. So apologies for the delay there. But just taking chair privilege, really. Just to ask a question to both of you. You mentioned about a lot of discussion here about the scenarios, and I've been aware, because I was involved in an IPCC workshop on scenarios for the AR7, the 7th assessment report. You know, there's the RCP scenarios are there. The TCFD recommends, the Task Force on Climate-Related Financial Disclosure recommends using the high one or the low one, depending if you're looking at physical or transition risk. Paul, you mentioned that some users want exotic scenarios. It'd be interesting to find out a little bit more about what is meant by that. But also, are any end users at the moment looking at combining the RCP, i.e. the the physical scenarios with the shared socio-economic pathways to demonstrate how that changing economic and social environment may impact on the range of risk associated with a specific hazard.
That's a question for me, sorry.
Or both of you, really, yeah.
Yeah, Ben, sorry, you go.
So firstly, we can find scenarios that are consistent kind of within the RCP, our previous projections based on the RCPs that are consistent with the SSP, so produce similar values, and we can kind of use the same approach for both the kind of the socio-economic pathways, but also warming levels. So that's something that we could do because there's an increasing demand for information about warming levels. The only place that I'm aware where the socio-economic part affects sea level is the varying assumptions about population changes affects the estimate for the contribution from groundwater, which is quite small for the UK, but is relevant for, say, South Asia. There is a lot of information within there about kind of regional differences to population that aren't kind of included in the way the projections work, at least, you know, as things currently stand. So I guess that's my kind of perspective. Hopefully that's answered part of the question.
Okay. Thank you. Paul?
Yeah, so exotic scenario. So there's a kind of a flippant comment. What I mean is, I guess from my academic world, which was sort of in RCPs, SSPs, you're getting so the so-called NGFS scenarios. So again, not to get too much on the alphabet soups, but these are ones that tend to describe in the financial industry, and they often work around global warming levels and assumptions about what we're kind of committed, what pathways we're committed to. So I think the from nationally determined contributions we're on for a 2.7 degree warming, then they might have a more optimistic scenario, which is like 1.5 degrees, et cetera, and we do global warming levels. There are the shell scenarios as well. I've mentioned in passing, but no one's ever really asked for it. But yeah, but those are the other scenarios, and those who are interested in that world. Very quickly on you asked about SSPs and RCPs. I think, yeah, I mean we're typically working in a way that we're just interested in how the hazard scales, which is essentially a function of global mean surface temperature to massively simplify it. So the storylines that are provided by those SSPs, and by the way, I love storylines. The storylines that are provided by those are not something that we're seeing people connecting to a huge degree. I know others like us will be offering like flexibility in like the catastrophe modeling framework for like to play around with defenses, but then you or vulnerability. So like what does a house in 2050 look like? This typical house in this location, is it more or less vulnerable to the floods that you might expect? I think some of the difficulty is for us, we because we work at the asset level, it's kind of knowing what does SSP 5 look like for in terms of building regs for Lincoln City Council. It's like, so that doing something sensible with that information around vulnerabilities and exposures, I think is a challenge. So at the minute we're kind of just offering sort of flexibility to explore that. Of course, we can say something about, we can look at where populations are and say something about from using the economic information. I don't know if that's quite answered your question, but
thank you. I'll just there's a question here from Andy. Andy Beverson, thank you for this. So, which data from UKCP? Which data from UKCP is typically used in the catastrophe modelling JBA does, and does it make a big difference? Some UKCP data and products are better suited at representing small scale processes, and that cause localized extreme impacts. So does it, are you seeing much variation in the range from the range of products that UKCP produces? And if there's a future set of products, would that compound issues, or would that make things easier to explain and better to understand?
So I think Andy's, I believe, referring to this UKCP, as you mentioned, UKCP local, which are the available at 2.2 kilometer resolution. So we are making use of that data mainly with our sister companies, doing a lot of work with that. And in fact, some people in JBA Consulting were involved in developing that data. The difficulty for us is that it's only available for a limited number of scenarios at the minute. It is something that we're trying to include, because absolutely we want to have a better representation of how, for instance, convective rain will change going into the future. As in general, I think it's a question, how is the information used? So without getting into the weeds, we have in a catastrophe model framework, we have our thousands of years of weather events. We use information from changes in the extreme value distribution to effectively rescale those our what's called an event set, multiple thousand-year event set, to come up with things which are larger, longer lasting, depending if that's what the numbers show. So it's yeah, without getting into more details, but maybe that's probably enough information. But if someone wants to ask me more, I'm happy to fill them in.
Okay, thank you. And this question that was initially from Michael Kendon, that were initially aimed at yourself, Paul, but it's very relevant to what Ben has discussed. Also, was on my list of questions about Antarctic warming and Antarctic melt. The estimates, Paul says, the estimates for RCP 8.5 out to 2300 are for up to as much as 5 meters, probably even more, of sea level rise. So how to quote Michael directly, how on earth can the risk management community and insurance and reinsurance industries possibly handle this? Thinking of London, many buildings are centuries old, there's some even older than centuries. Is London's future shorter than its past? That's a philosophical question at a critical time.
So credit, I think if Michael said me showing the numbers, they were from Ben. So I mean, I just say quickly, Ben, I'm sure you should come with your view too. I think that we're going through, there's an education process. I feel, I've just joined this industry from 20 years in academia, so I'm also on a very steep learning curve. But I think the engagement with scenarios is still quite new, and climate change in general is quite new. Many of you will be familiar with this report, the Emperor's New Climate Scenarios, which was you can tell it's on my desk or anything, and I'm having a lot of engagement with that. So in summary, that sort of talks about how these climate scenarios can lead, just a straightforward reading, as like Ben shows, the central estimate is can quite misleading in terms of what the risk actually is, and I think essentially there's a risk, and I think probably actuality that people in the industry are rather too sanguine about what's happening. I can even say, like, from a flood point of view, someone can look at our data and go, oh, wow, actually the flood risk decreases in my house there. And I was like, well, yeah, but the rest of the world is on fire and your supply chains have collapsed, and so this sort of more of a not only these kind of more extreme scenarios, but a more holistic view of risk, I think, is something we need to take into. How's London going to deal with it? I can't answer that. I think, but a better, for me, a better kind of facing up to these possibilities is definitely what is needed. Ben.
Thanks, Paul. I think part of the role of storylines is just to kind of, like you say, get away from just looking at the kind of central range from the projections, and actually kind of firstly say we've had to make kind of assumptions about the relationship between warming globally and Antarctica to kind of get those probabilities in the first place, and secondly to look at kind of the real possibility of quite drastic changes, because it's not that wouldn't involve kind of incremental changes to existing plans. It would mean something entirely different. So that's where I kind of see this work, but I'm not. But practically, I mean, I'm not an engineer, but yeah, it seems like 5 meters. That's not a lot that could be done. You'd be really having to make some really difficult decisions about what you do in those situations.
Okay, thank you. And just running short time, but the questions that I haven't been able to get through on the chat, hopefully I'll make sure Ben and Paul get access to those and they can reply. But just there's one here that I find challenging as well. So this is from Dave Haverson about the 8.5. So David says seems to be a growing feeling that the RCP 8.5 seems implausible. What's your thinking on this, and what do you think the future maximum scenarios will look like? Now, I've been involved in this sort of stuff for quite a while. So my view is that the 8.5 is probably the most plausible one of the lot at the moment. We've got to remember that all scenarios have got to be treated equally. think as Paul mentioned about people always look at the central estimate and think that's the one we're going to get. But at the moment, if we look at the key indicators, global temperature, sea level rise, global ice melt, etc., they're all at the high, the Antarctic and Arctic sea ice extent, they're all at the top end or even above what the scenarios say. We're underestimating some of the key feedbacks within the climate models. The models themselves don't include, I believe the climate models don't yet include feedback from melting of the permafrost and methane release from permafrost. So there's certain key elements that are still not fully represented within the global elements that are still not represented in the climate models, let alone some localized feedbacks as well. So my personal view, based on my understanding, is the 8.5 is probably the most, it's a pathway we're following. It's one we've got to bend the curve on very rapidly. But I just, Paul, Ben, your thoughts on that?
Happy to. I mean, I think for me, the key point here, I think a lot of the discussion around this was around the detail of what 8.5 looks like socioeconomically versus exactly what you've been talking about, David, the physical impact. So I think there's been a big disconnect. So yeah, I think there's definitely debate to be had. Like 8.5 says that we're going to be using a ton of coal. The global economy is going to grow like this. Fine, that's maybe that isn't going to happen. But for all the reasons you've just said, what is projected from models running 8.5 cannot be ruled out, because we know we're missing feedbacks. We know models have been coming up short and underestimating. So I think we need to kind of reframe the discussion. So we shouldn't be throwing out the baby in the bathwater. Basically, the information that's come out from models running that scenario is probably the best information that we've got about pushing some of the edges, pushing the extreme. And obviously, I come back to the point about storylines as well. Even within 8.5, different models are going to give you a range of different answers, and you want to pull out, as Ben's been saying, those ones which are physically plausible worst case scenarios.
Okay, thank you. Ben?
So just a few comments on RCP 8.5. I think for the next kind of CMIP 7, there's a discussion that for the reasons kind of Paul described, that we might not see a kind of an equivalent to 8.5 watts per square meter in terms of what the actual extra forcing is. However, the uncertainty comes from how kind of the elements of the climate system that David mentioned actually respond to the warming, and for where there's a kind of feedback or a kind of runaway ice sheet contribution, for example. Once that's triggered, the actual warming, the subsequent warming isn't as important. It's the trigger points that matter. So I guess it's reframing it in terms of thinking about what the kind of future impacts are, rather than getting too hung up on kind of a number where the relationship between that forcing and how the actual climate response is not kind of well understood.
Okay, thank you very much. Look, just bearing in mind time, I'll have to call that a day here on questions. So Ben and Paul, thank you very much. And for those people who've put the questions in, thank you. And sorry for those I haven't been able to get around to asking. I was wondering about future plans. So again, I'll discuss that with my co-chair and the UKCP panel at the Met Office to see what we can do about communicating what's actually going to happen. There is, of course, depending on funding and a lot of other things in place to make sure the next round can be done in a satisfactory way. But the next webinar is on the 26th of October. We've got two presenters there, two guests, Paul Buckley from CFAS and Victoria Ramsey from Met Office. Paul's talking about climate risks in the UK marine environment. I'm very happy to be listening to this, because this is based on the Marine Climate Change Impacts Programme, which on my days, I'm showing my age here. I was a co-PI on that project in 2006, I think it was. And then Victoria is going to talk about the new rainfall guidance from UKCP for using rainfall data. So that looks very interesting set of talks. Please feel free to share, once we announce this formally, please feel free to share with all your colleagues. I think one of the powerful things here is that what we want to do from the UKCP programme is to get and solicit advice and responses about what needs to be done, where the gaps are in what data being provided, and what technical advice is being provided. So the more people we can get to give us that advice, the better, and we can help improve what we're doing with the current set of UKCP data, but also future work as well. So, and I'd also just like to take time to thank Vitaly, Nia, and Victoria on the on the UKCP team for getting all this together and getting me organised, which is quite a task. So, look, everyone, thank you very much. And thank you very much for your time over the last hour, and look forward to speaking to you all again and hearing from you again. So, thank you very much.
Thank you.
Bye.
Cheers. Bye-bye.
Bye. Thank you.